Good afternoon, this is Andy Schweitzer, and this is a video on sort of a little more extensive on the Lewis dot structures. Now, this is a topic that we do not cover in honors chemistry, so if you're coming through honors and you're going to AP, you'd want to kind of pay attention a little more about this. But here's an example we would do in honors chemistry. Let's say we have the molecule sulfate. I want to create a Lewis structure. Okay, and we'll cover a couple of rules here for doing this. I'm just going to copy these off the previous screen because they're all right here, and I'll just do this, copy and pop them down here. Okay, and paste. All right, there we go. That is the instructions that an honors chemistry student would get, and we follow these directions, create little molecules, and if it works out, it works out. That's all. We don't really question it a whole lot. So number of electrons in inventory. So sulfur is going to have 6 valence electrons. The oxygen has 6 valence electrons, and they're times 4, 12, 24 electrons, and then so it gives me a grand total of 30 plus the 2 from negative charge gives me 32 electrons. Now, for this, we build a skeleton structure. So the sulfur goes in the center, oxygen, 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 and oxygen. Okay, we start adding electrons to fulfill the octet duet rule. Okay, so 2, 4, 6, 8, and we get 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. All right, it fills up nicely. All right, and therefore we get brackets, and we put our -2 charge, and at this point, honors chemistry student walks away thinking they're good to go. All right, then we might look at a chemical. Let's say it would be H2SO4. Okay, now this is a strong acid. And it's okay, well, same thing. We got our the 6. We got our 6 times 4 is 24. Add them all up. We got 1 times 2. So we're going to get now a whopping 34 electrons. And it looks like this. Sulfur, oxygen, 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 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. But I wanted the 2 hydrogens, so I'm going to take this guy here and just put a hydrogen right here, and I'll pick another one over here, and single bond to a hydrogen. Okay, and you'll find that there is all the electrons are in fact here. 2, 4, 6, 8. They're all here. So we have 34 electrons now. And you might ask yourself a question, well, what about these 2 oxygens on the other side? Like, as in, maybe those guys should also be able to hold hydrogens. So you have to start asking yourself some questions and say, okay, is it in fact correct? In nature, do we have H2SO4 or do we have H2SO4? Because technically, the way you're drawing this, I should be able to slap a hydrogen on here and here. So H4, but we don't have that. We have H2SO4. So maybe there's something different about those other 2 oxygens that's not the same as with the other 2 oxygens. So a couple things I'll point out here is that one, the sulfur, okay, sulfur is in the 3rd row. Okay, that's important because now there's more options for sulfur, meaning sulfur can hold more than 8 electrons. That's important because if it was in the 2nd row, 8's the max and it has no more options. Okay, but students will very often start experimenting with double bonds here and triple bonds within the sulfate, and they will find that they do get different options and they do work. So that is ultimately where we use formal charge to deviate from a simple drawing like this to something that might be a little more realistic. Okay, So one, sulfur's in the third row, so it has more options. And again, the other is there a Lewis structure that might be alternate? It might also work. Okay, so which one do we choose? That's really what we're going to use formal charge for. Formal charge is a mathematical description of it's man-made. Now I'll clarify, this is man-made mathematical relationship. So with that said, it's used to help describe what's going on. Now let's try an example here. Now the sulfate. Okay, we have this option here, which I just drew. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Okay. And let's try this option. Sulfur. Now, in a Lewis structure, we should have the correct number of electrons. 30 should be 32 electrons for this guy because the sulfur contains 6 valence electrons, oxygen is 6, and then grand total giving us 32. So in this case, we have 2, 4, 6, 8. 8 times 4 is 32. And here, do I still have my 32 here? And I think I need to get my eraser out because I inadvertently added an extra electron. I'm not going to do that. I'll just cross it off here. There we go. When I made my double, I got to delete 2 of them, just like I did here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So there's still 32 electrons here. I basically took 2 off and created a bond. Is that legal now? Well, sulfur can hold more than 2 electrons. Okay. So we have 2 options here. Which option are we going to assume is better? Okay. So we use formal charge for this. Now, we'll also premise that, okay, for those of you in my class, that formal charge has been eliminated from the AP curriculum for a while. You will not see it on an AP exam. Why? Well, they don't exactly explain. They would. You can go to various conferences, and you can get all sorts of reasons as to why they might eliminate this. It is a very critical part of just writing out Lewis structures. Sometimes they eliminate things if on a higher academic level someone might have some disagreements about why things happen. So this is a man-made mathematical relations, and maybe at some point they just disagree with how it actually works. But in the sense, it is there, and I don't use it in my lower level chemistry classes, and it will not be on your AP exam, but we will use it and discuss it as something you will see in college. So the way it works is you assign a formal charge for every single atom. Okay. So it says how you do that. So it's the group number of electrons. Okay. So I'm going to do this oxygen. Every oxygen on this thing here, find my cursor, will have the same formal charge because they're all bonded the same. So it is the number. It's the number of electrons. So the number of valence, as we mentioned, was 6 minus 1/2 times the number of electrons in covalent bonds. Okay, so 2 electrons are in times, so it's going to be, let's just put this out here, so it'll be minus 1/2 times the number of, so 2, and then minus the number of electrons in lone pairs, 2, 4, 6. That would be 6 electrons. Okay, so it's going to be, in this case, this would be 6 minus 1 minus 6, okay, would be equivalent to a negative 7. Now it says, remember these electrons are shared, okay. Formal charge equals, it's the same thing here, so formal charge equals the group number minus the number of covalent bonds minus number of electrons in this. Okay, so 6 minus 1 minus 6, okay. equals a -7. All right, -7, -7, -7, -7. Now the sulfur, this is for the oxygen, is going to be, for the sulfur, will be equal to, the group number is 6. Number, again, this is just a little bit more way to look at it. Same thing. Group number 6 minus the number of covalent bonds, which is 4, minus the lone pair, which is 0. So this is going to be a -2. And you can assign your little, on your own. This is not part of the Lewis structure. You would never include the formal charges on here as far as the actual structure is concerned. All right, now let's do this guy. Okay, the oxygen. Okay, now this oxygen right here is going to be 6 minus the number of covalent bonds. So that's going to be, there's 2 of them there. So 2 covalent bonds. So -2 minus, again, actual number of electrons would be 4. Point. 6 minus 2 is 4, and -4 equals 0. So this now has a formal charge of 0. And this guy here, also formal charge of 0. This one here would be 6 minus 1 minus 6. All right, so 6 minus 1 is a 5, minus 6 is a -1. So -1 here and -1 here. And here we have sulfur. Would be the number 6 minus the 2, 4, 1, 2, 3, 4, 5, 6, and then it would be again 0. So we have much lower formal charges. Therefore, we have this sulfur with a double bond one, double bond on the other, with formal charges of 0. And then we have a single bond one way, and this is going to give us 1, 2, 3, 4, 5, 6. Now, the formal charge could be listed as a slight charge of, like this, -1. That's not a full charge, a partial charge. Okay, 1, 2, 3, 4, 5, 6, partial charge of -1. And notice that your partial charges add up to -1 plus a -1 equals a -2, which is the actual charge on this compound. And I am going to say these are not included on there, just so you know. This would be the better structure. Okay. Now, this also validates the fact that we have H2SO4. So H2SO4 looks like this. The oxygen and put the rest of my electrons in. All right, there you go. Formal charge, something to mess around with and something just to be aware of. Thank you.